I'm Hervé Boeglen. I'm an associate professor at the University of Poitiers, which is in the west of France. I work also at the Xlim laboratory. So I would like to present you something that was hard for me when I started the tutorial. I'm an electronics guy, so I'm not really fond of computer science. So when you start with things like that, it can be quite tough. Well, it's a question of time, in fact, to get accustomed to the system. And GNU Radio is really powerful, but it's something also that's quite complex. I noticed that in the last group because I did about 1/3 of what I expected to do. So, well, perhaps you'll be faster than the others. I try to not to make the same mistakes as I did with the others. Anyway, so let's start with what I would like to show you. So, in fact, I'm going to talk about a Nordic Semiconductor, which is some people already know them. They are from the north of Europe, and they are semiconductor manufacturers, and they're very well known in the IoT field because they've got chips that are really interesting that you find in a lot of products, especially in sports, keyboards, wireless keyboards, mice, drones, etc. So they've got a proprietary protocol, which we are going to see, and we are trying to decode and to replay it with GNU Radio. So our goal is to build a transmitter and receiver. So when you start with that, you say, oh, should I start from the beginning doing my own OT module? And most of the time, no, because when you think about something, you know that on the planet someone else has already think about the same and started already a certain work. And that was the case for this solution here. It's an American guy working as a specialist in the security. He does a lot of challenge in conference for hackers, and he's quite good. So he did an OT, he built an OT module called GR Nordic, and we're going to start with this module, and we're going to change certain things in the module to adapt it for our needs. Because as you will see, it doesn't exactly work as it should, and even it's got bugs, so we'll try to go inside this to build our module to suit our needs. So that's the third part, and after that I finish with a conclusion. So what I noticed in the other group, it was obvious for me since Tanguy did that this morning. I thought that everybody was adding in his head the organization of an O3 out of 3 module in GNU Radio with the different directories and things like that. Apparently it's not the case for a lot of people, so I had to explain some things about that, though, well, because some of you are probably geeks in GNU Radio, some of us not. So if I go too far or too slow, don't hesitate to tell me, okay? So, for people who have already worked in embedded systems, you probably know this module. You find it on Chinese websites for less than €1. Something surprising because when you try to build to buy the original chip from Nordic, it costs you €4 to €5. So how the Chinese are able to go down as that is simply because these are not original chips, they are fake. And in fact, there's someone that just dismantled the circuits and with a microscope had a look on what was inside. And the original one is manufactured with a 250 nanometer technology, whereas the Chinese one is with an oldest technology in 359 nanometers. And also, be careful when you buy these modules. They have not exactly the same performance than the original. If you expect to have a certain distance, communication distance, the Chinese ones are not good, and especially the antenna is just bad. But for something like between 5 to 10 meters, that's okay. So be careful about that. That's exactly this chip that we are going to mimic with GNU Radio. So what do you find inside this chip? Well, it's already something that's quite complete. You've got the transmitter part with the power amplifier, a TX filter, and its GFSK modulation, okay? And the same with the receiver with a low noise amplifier and the demodulation stages. And the baseband part is something really interesting because it deals with the packetizing side, and it's quite easy to use. You communicate with this chip using the SPI protocol, which you find on most microcontrollers. So this chip is quite well known and really used a lot for a lot of applications. So these are the main characteristics summarized. You can go up to 2 megabits per second for the data rate. The maximum output power is 0 dBm, okay? And the consumption is quite low because it's for embedded systems. And the sensitivity also is quite good. So if you don't add a power amplifier with a good antenna, you can have something that's about 95 dB of link budget, which is quite interesting. So the payload is limited to 32 bytes, okay? That can be a drawback in some applications. And the voltage, so the voltage range it goes up to 3.6 volts. If you want to have more details about this chip, you've got the link for the data sheet that you will find on the internet. So the protocol we are going to build here is, in fact, what they call the enhanced shock burst protocol. So it means that when you use this protocol with the chip, you've got a packet with these fields. So the first field is the preamble, which can be either OX55 or OXAA hexadecimal, depending on the address. If it starts with a 0 or a 1, and the address side field is can go up to 5 bytes. So a transmitter or a receiver has got an address, and this is sent with the packet. The packet control field is something they've added in the enhanced version. It gives you the payload length. 6 bits means that you can go from 0 to 31. Okay, so 32 bytes in maximum. The packet ID, that's a feature also. The transmitter can send several times the packet, up to 4 times in fact, and that's the packet ID, which is incremented from 0 to 3. Okay, and there's also a nice feature. You can have an auto acknowledge in one of the communication possibility, and this is the bit you set. If it's set, it means that you acknowledge. You expect the receiver to acknowledge the packet, so it sends a packet to say, okay, I've received the packet. Okay, that's on 1 bit. We are not going to use this here. Okay, the funny thing, also one of the reasons I wanted to go a bit more deeply inside the thing, is that you can have an NRF24LU1 plus, which is an NRF24L01 plus, just the one we have seen, plus an USB full-speed chip, plus a microcontroller, AT51. It means that in a USB mouse key, you've got this, and you can change the firmware and use this as a transmitter, as a packet sniffer, and can be quite interesting. So if you've got this kind of dongle with an old mouse that doesn't work, don't throw it away, keep it, because it can be a transceiver for the 2.4 gigahertz band, because it's got a mode where you can send a sign on the different channel, so that's quite interesting. It has to be a unified dongle. It's a special type. I say a bit more about that later on. Okay, so the NRF24 has been phased out by Nordic, and now it's replaced by the NRF52 series. They're still compatible with the old chip, but they do more things. They integrate a microcontroller. It's an ARM Cortex M4 in all these chips, and of course they can do Bluetooth, they can do NFC, ANT+, several other protocols, and it's not more expensive. They are really flexible. If you want to play with this, you can buy a development kit like this one. For 40 euros, you've got the development kit with the NRF52, and you've got the JTAG debugger already, a J-Link that you can use for other boards. And you get also 10 samples of the chip. So when you see the price of the chip, 10 samples would be more than 40 euros. So it's quite interesting. And there's a lot of documentation about that. If you want to look, they've also developed a lot of applications on smartphones to play with Bluetooth Low Energy. And it's really nice. Nordic hasn't given me any money for that. So it's not an advertisement. So where do we find an NRF chips? We talked about with Leo about that. You find them also in drones, like this one. So you can play, trying to decode the protocol with this drone. You find them in bike computers, in watches, in keyboards, mice, and in a lot of devices which need a wireless connection. So you find them in a lot of products. So that's why it's interesting to study them. So it's a well-known technology. I found quite a lot of resources about AX. The packet communication is also something interesting and not something easy in GNU Radio. That's also why I wanted to fiddle with this. So the goal of this tutorial, if you accept the mission, is to build a Nordic NX shockburst compliant transceiver with GNU Radio. So I've got two boards fitted with an NRF24L01 plus that I will put in the room, so you will be able to see if your receiver is working or not. Okay. So for those interested, I'm quite fond of STM32, so it would work on an Arduino, but I've done the code for the STM32 and also the board for those who want to build the board. I will give everything, okay? So let's have a look on what's available for our system. So the question, do we have to start from nothing? Thanks God, no. But anyway, there are not so many up-to-date implementation. I found the one that we're gonna use now, and also an older one, which was for our Texas Instruments chip. It's quite old, 2014, so some of the blocks are not compatible with the new versions of GNU Radio. But it's interesting to see how they build the thing, especially using messages. So the module we're gonna fiddle with is the one that's built by Bastille Research, called GR Nordic. It uses the GNU Radio message passing interface, okay, not streams. It has been designed to identify vulnerabilities of wireless keyboards and mice, and it's been presented, well, what they call mouse jack. It has been presented in DEF CON 24. It's a hacking convention by Mark Newlin from Bastille Network. He's a specialist of security, working normally also with DARPA in the USA. So, in fact, he identified quite a few vulnerabilities in wireless keyboards and mice, and he started a work on that. And thanks to him, the Logitech and Microsoft changed their system because of the vulnerabilities they showed. So that was quite interesting. It's not only hacking, it's also helped to improve the security of the system. So especially if you say that to someone who wants to hack something, he starts with this type of message. Okay, I start tomorrow. Because since the displacement of a mouse would not give any useful information to a hacker, the mouse reports are not encrypted. That was in 2009. It's no longer the case now, but see. So classically, with a wireless, it's quite handy, wireless mouse. So all the movement and the clicks are sent by radio to the dongle. Same for the keyboard. So in fact, thanks to the USB interface, you get the packets, and the PC treats everything so that you've got everything on your screen. And what you can do as an attacker, you can talk to a dongle, but also more interesting, you can eavesdrop on an unencrypted keyboard and get the passwords. Okay, so quite interesting. If you want to have more details about that, you've got the link of his presentation to DEF CON, and it's really interesting because it details everything. Okay, it's time to work. So first thing you'll have to do is to get the GR Nordic 003 module, just by the command git clone. Should work with no problem. So if you are lazy, like me, and you don't want to tap everything, just open the navigator, go to Google, you tap GR Nordic. I know the navigator on the virtual machine is Dilo. Everybody knows that's what means -J2. Just a simple example, when you install GNU Radio from source and you just don't use this option, you just type make on a powerful PC, it can take more than 2 hours to build all the system. If you've got a Core i7, you've got 8 threads on the processor, and if you type -J8, it takes only 15 minutes. Because make has been parallelized on the new Linux distributions. So if you've got a processor with several cores, don't forget this option, because in terms of time, it's interesting. Doing these commands means that you're going to have this out of 3 module installed on your system. And normally, you will see that some blocks will appear in GNU Radio Companion. So if you've already finished that, try to look, you open GRC, GNU Radio Companion, and have a look to find the blocks. There should be 2 new blocks. Okay, so for those who have tried to get the blocks and to put them into GRC, it doesn't work. Okay, it's normal, because these blocks haven't been written by the authors, so we'll have to do it. It's a pity. The XML files.
Okay, they are missing the...
Yes. Well, you've got the template, but nothing has been done for that. Well, it will take a certain time, but anyway, I'll give you the codes. So, okay. Do you know how to, starting from a new block, reading the I/O signatures, how to adapt the XML file according to that? How do you make the relation between the GRC blocks written in XML and the C++ or the Python written blocks? Do you know how to do that? Okay, so we'll have to do that. So if you look here, what you should do first, well, because that was a problem with the other group, so as I remember the problem, when you did the command git clone, you got a lot of new files on your PC, and the architecture is always the same for an out of 3 module in GNU Radio. I suppose that you know these subdirectories. The first one is the lib, where you find all the C++ blocks, okay? Include all the headers related to these blocks, okay? GRC is the directory where you find the XML files that GNU Radio Companion will use to draw the blocks with the input outputs. What else? If you write blocks in Python, you will have in this directory Python files, okay? And something Tanguy already talked about that this morning, so I won't go further. Everybody knows what Swig is. Swig is a wrapper which allows Python to talk with C++ blocks. Okay, so that's an important directory. You will find, of course, the build directory where you build everything with CMake, and also the CMake directory where you've got all the definition files that CMake uses for the compilation of the module. Okay, so let's have a look now in the lib directory, and in the lib directory, you will find C++ blocks, okay? And there's one that we would like to study, because when you start with an OT module coming from the web, it's always interesting to see how it has been written, and especially the inputs and the outputs of the block, especially since you've got to build your GRC blocks, okay? So let's have a look on this one. This is the Nordic TX, okay, that's the transmitter. So what about the input and the output? Do you notice something particular for this block? 0, 0, 0. Yeah, 0, 0, 0 for the input. So suppose he hasn't got any input. It's not true, because in fact, when you use the message passing interface of GNU Radio. You find the input here, okay? But it works independently of the rest, okay? So it doesn't go in the I/O signature for the input, okay? Can be the same for the output. But of course, for the output, we've got something defined here. It can have multiple outputs because I've got a variable called channel count. So apparently this system is able to send packets on different wireless channels. Okay? So our GRC block should be configurable. So if we want to choose 2 outputs, it should work normally. Okay? We'll see how we write that. So just a little thing with, for the message passing interface, it uses PMTs. So a bit strange things, but well, something quite interesting. I'll talk a bit more about that afterwards. So in fact, when you've got a message as an input, you've got to have a function which is called a message handler in your code. So this message handler, every time a message comes in, its role is just to treat this message. Okay. So if you look further in the code, you will find that because you have to do a bind, and the function is called Nordic Tap message handler in that case. Okay. So with the I/O signatures, we are able to write the XML code for the GRC files. Okay. I won't ask you to do it. I'll give you the code. And the other one, just to see the RX. So the RX, we've got a bit more things. So it's just the reverse as the other concerning the I/O signatures. We've got something which is a stream in input, but output we haven't got anything. It's in fact again a message port that's for the output. Okay, so we'll have to deal with, on one side, streams, and the other side with messages. Validations, sorry. There's a missing S, so the new one is already on the site. Okay. Yes, that's right. So every time we do something, it's V1, V2. Okay. So you've got the things that are okay. Okay. So normally you should be able to modify the XML files to so that they work in GRC, but I gave you the solution. You've got this in the V1 subdirectory in the archive. Okay. So just remember that for the public constructor, the make function you find in the C++, you have to find it here. And when you've got parameters like here, we've got a variable. It becomes a parameter here, okay, of type int with a default value which is 1, okay. And funny thing, the number of ports at the output can change thanks to the value of this variable, okay. So that's the Nordic TX block. So no. What do you have to do? You take the files you find in the V1 subdirectory, you copy them in the GRC subdirectory of your module. Okay? So you replace the old one by the new ones. What do you have to do after that? So, yep, you have to go for a build again, okay, so that it's recognized by GRC. Okay? Don't forget that every time you've got a modification like that, you go into the build directory again, and you start a new build. CMake is a system that builds all the make files all the files you need to compile something, okay? And the make command does the compilation and the link to have an executable at the end, okay? So CMake just looks, apart from creating the make files you need for make, it looks also on your system if you've got all the dependencies you need to build a module. And so if you have done CMake already and you've got everything on your system, you don't have to type CMake again, okay? After that, it's just make. So what's inside when you unzip this file, you will have a steps directory created, and inside this directory, you have got all the solutions of the thing you have to do during this session. So when it's V1, you've got already the correct files that you can copy, so you don't have to do the job, in fact. Okay? So for example, when on my slides you see V1, it means that in the subdirectory V1, you've got this file already. So you just have to copy it inside the GRC. So if you want the slides, to look at the slides at the same time, yeah, they are on my website. Okay, so that's what we have to do to make these blocks available to GRC. So you just copy the two files you've got in the V1 subdirectory into the GRC directory. When you've done that, you go to the build directory and you start again a make and a sudo make install. And then you refresh into GNU Radio Companion and you will see the updated blocks, and you should see the blocks, the working blocks. Okay? What we want to do is to try with the code that's already existing. You've got a directory called examples, so it could be nice to try with this. I've got two STM32 with the modules, so I'll put one here and the other on the other side, so you can check your receiver with this. So how is the packet, the ESB packet constructed? My STM32 sends a packet every half a second, okay? So the payload is supposedly the room temperature, but you'll see that's to refresh you. It will send you 20 degrees. It was just to test the code so that the temperature wasn't changing, because I wanted to see exactly what I get inside the packet. So, but it's not a problem because I've got temperature sensors on the boards anyway. So the address is OX55 5 times, okay? The payload is 8 bytes. In the payload, you've got 4 spaces plus the temperature in the form xx.x, okay? So in our case, it's going to be 20.0. The CRC is going to be on 2 bytes. That's something you can configure on the NRF 24. The data rate is going to be 2 megabits per second. And the RF channel I use is the channel 85 because I want to be outside the Wi-Fi band, because when you fiddle with these modules and you've got Wi-Fi, it's going to be a trouble. So up to 2.8, yeah, it's okay. Wi-Fi is just under. So that's why I chose this channel. So okay, let's go with the transmitters. What we want to check now is the receiver, and there's a nice example in the example directory called Nordic Receiver. So open this file and don't be as lazy as they were in the other group, because if you tap on only Nordic receiver and you forget the arguments, it's going to look at channel 4 by default. So when you open a Python file you don't know, check, look at the code, and especially the input arguments. And that's normally at the end of the file. So I'm going to open the file to show you. I've got more examples because I did some things myself also. So it's the one is Nordic Receiver. So first thing that you'll have as a problem, they say that this OOT, so exactly the term they've used, it is supposedly SDR agnostic. What does it mean? It means that they use the Osmo SDR library, which works with USRPs and a lot of other devices like RF and things like that, but not with the add-on Pluto. Yeah. So what we have to do is to change a line into this code, to this file, so that it works with our Pluto. Okay? So you have to modify Nordic _receiver .py, sorry, and add a line so that your Pluto is recognized. So you have to comment all the things that deal with Osmo SDR, okay, and replace, add a line to add a Pluto source with another problem. On my machine, I don't have to precise the IP address, but you will have to precise the IP address. You've already the solution in the V2 directory normally. Okay. So if you are lazy, you can directly go to the modifications. It's in the subdirectory V2. Okay. Don't forget, change this line, and also to add the line to import the IIO library from analog devices. Okay. Another thing I've noticed with the other group is that people are not, some of them are not really accustomed to how a Python file for GNU Radio is built. You've got a lot of information about what's inside the file and what it does, especially when you look at the connect keyword. Okay, you see that, for example, here I start with a Pluto source that I connect to the input of a LPF low-pass filter. This low-pass filter, the output of the low-pass filter, is connected to the input of the GFSCAD demode block, and the GFSCAD demode block goes to the RX. And don't forget to read the arguments at the end of the file. So, as you can see, it works. You see the sequence changing. So channel 85, those. So for those who want to test, I can bring the board nearer to your Pluto. So what it's trying to do is to bring everything into GRC, but well, yeah, the Nordic Tap printer, it works in the Python code. There's a function for that. And what we want to do, that's the next thing we want to do, is to add this block and make it available to GRC. Because of course, well, if you like playing with Python is cool, but in GRC you've got a lot of interesting blocks to look at the signals and things like that. So it's quite nice to have everything into GRC. But already we've checked that it works on this channel with the receiver they've built in the example. So now we've integrated our Pluto. We've checked the receiver. It works. Okay. An important thing to know is how do you demodulate the signal sent by the NRF. Is by looking what they do here in this Python file. Of course, you need your Pluto, low pass filter just to limit the bandwidth, so to increase the signal to noise ratio. Okay. Then you do an FSK demodulation. Okay, you've got a block for that in GNU Radio, and finally, you go into your block called Nordic RX, and that's the result we had in the terminal. Okay, so that's the blocks we will need in GNU Radio Companion. Okay. So there's one missing block. Is this one? See, because the RX has got a message output port, and apparently we need something called Nordic Tap printer. Where is this Nordic Tap printer? In fact, it's in the file Nordic Receiver. It's a function they've done. Okay, so you see class Nordic Tap printer. Okay, so it's already implemented here. The trouble with that is that, again, the mic, it's not available in GRC and in other blocks. It's a local function. That's not nice. I would like to take this function, make a block, and this block bring it to GRC. That's next job. Okay, so it's quite easy. I'll show the procedure, and after that, either you code or you get the V4, I think. Okay, so the idea, everybody is okay with this? I need this block so that I can do the same in GRC. Okay, so the code is quite nice. It's already a sync block. So what I can do is simply go into the Python directory, okay, of the GR Nordic module, and create a new function called Nordic blocks. And inside this Nordic blocks.py, I'll put the code of the Nordic Tap printer. Okay? But I've got to change a few files so that the build system knows what I have done. Okay? So in fact, I will have to change the cmakelist.txt. Okay? This one. I will have to add Nordic blocks.py. Okay? It's not finished. I've got to change another file, which is the double_init_.py. Don't forget this one, it's important. And here you have to add from Nordic blocks, which is the name of our Python file, you have to do an import of Nordic Tap printer. I've already done the Nordic Tap transmitter because that's the next step. I put the two blocks inside the file. Okay, so these three files. The first file, Nordic blocks, has to be created. You put the function in it, which is also a block, in fact. Then you modify the cmakelist.txt, and then this one as well, and it's not finished. You'll have to create an XML file so that the block can be recognized by GRC. And normally you've got everything in V4. V3, that's right. Have a look, but normally it should be corrected. The XML file, there was a line that caused the problem. It should be okay now. I just open it. So in fact, either you modify the files I was talking about, or you take everything that's in V4 and you copy 3 of these files into the Python directory, and the 4th one, the GRC one, in the GRC directory. Okay? So to summarize, in V4 you've got 4 files. Okay? So 3 of these files have to go into Python. Okay? Python directory, so it's Nordic_block. That's the first one. The init has to be changed. Okay? And the CMake list as well has to be changed. The 4th file has to go into the GRC directory. Okay? And it's called Nordic_NordicTap_printer.xml. Okay? And I forget a last thing to change also. You've also to change the CMake list in the GRC directory. So good. And normally everything should be fine. So don't forget, in the CMake list that's in the GRC directory, modify it to add the new block. Otherwise, GRC won't see the block. You've got the blocks, so you're ready to build your flow graph to have a full receiver, GFSK receiver in GNU Radio Companion. And this is going to be something like that. So at the end, if I do the things properly, I should have my GRC model, which looks like that. So my Pluto. I've added something called a power squelch because, well, I want to decode a packet only when the power at the input is above a certain level. But that's normally what is done inside a real chip. Well, you have to try with the threshold values because it's not well documented. Well, you have to fiddle a little bit with that, but it works quite well. After that, you've got a low-pass filter. Okay, again to limit the reception bandwidth. You can take the ear block from the library if you don't want to see what this GFSK demode block does, but it's interesting to go to see what it does because in fact it uses these 3 blocks, and that's interesting to understand how GFSK demodulation works on a digital system. And the code is quite well documented and it's quite nice. For example, it gives you the explanation about the gain you've got to put in here according to the number of samples per symbol you've got. And of course, something really important in digital communication is to have the right rate. So you've got a clock recovery system. It uses the algorithm from Müller and Müller. It's very well known. It's a publication that you can find easily on the internet, and it's quite interesting. It's not so complicated to understand that. After that, you've got a binary slicer. So just to transform what gets out here into 0 and 1s. And the Nordic RX block, if you look into the code, it gets the 0 and 1, builds again bytes, and after that, it tries to recover a packet, okay? And then it prints it via the Nordic type printer block.
So the preamble is detected in the Nordic RX block then, from the bits to.
Here you've got a message which is a PMT with the information about what's inside the packet, the address, etc. And that's what is printed like here.
Okay.
Okay.
But the preamble and the address are all both 555. So if you have a distortion in the beginning, then you might see part of the address as the preamble.
Correct. Sometimes it doesn't work. It's possible. That's why, you know, using sequences like that, sending several times the packet, or using something about a bit more sophisticated. You send the packet, you ask the receiver to send an acknowledge. So you have to do that if you want to have a secure communication. Yeah.
I mean, there's a CRC, of course, so the CRC doesn't match them.
Exactly, CFC, the CRC is exactly here for that. So if I launch my model, I should get something working. Well, I had some nice things. The squelch block adds tags, which are squelch start of block and squelch end of block, and you can synchronize your time plot with this tag. Do you know how to do that? How to synchronize with a tag? Okay, I'll show you. So that's my GFSK packet. Okay. So yeah, what you can do is simply you go here. You've got trigger, okay, and my tag is squelch underscore SOB. So I say I want to synchronize on the squelch SOB. That's quite nice because you see exactly what you want to see and not the rest. Okay. Or sometimes you lose packets. That's possible. Huh? Okay. So you've got this model. You can use it if you want. Let's go for the next. So again, we've done now. We've got all the blocks for the receiver inside GRC. What would be nice now is to have the same for the transmitter. Okay. So transmitter is going to be a bit tougher because we are going to use the PMTs. Okay. Well, a few things about GFSK. I put that in the slides. So since we haven't got much time, you can look at it. You have the slides. Okay. So I just summarized, and it's interesting just to see how they've done it, because that's the theory, okay? But the nice thing is, how do you implement it in the digital domain, okay? And that's this information you're gonna find in the gfsk.py, okay? Same with the receiver. It's a phase shift discriminator, okay? And how do you implement that? Well, using this structure, it's quite nice. When you read the code, you find that they've done like that, okay? So it's interesting to read codes like that, because of course, you understand the way that you can do it digitally.
Is this a subsample delay or is this a single sample delay?
It's a single sample delay.
Single sample.
Yeah, yeah. So I've added also something if you want to connect this to Wireshark, because you see you had your packets, but at the same time, it sends to a UDP port the results, the decoded packet. So with Wireshark, they've implemented a Lua script that allows Wireshark to see the packets, decoded packets, directly from the Nordic Tap printer. Because we've seen what Nordic Tap printer did in the terminal, but more of that, it sends also to UDP port the packet. And these are the commands that you can use to see that in Wireshark. Okay? So it's quite nice. They've done an interesting work with this OOT module. So now, a bit more tricky thing is that the message passing interface uses the PMTs. And in fact, what I have understood about the utility of PMTs is that, well, in fact, it's quite logical. From a programming perspective, a message can be represented as a data type, simply, okay? When you are in Python, it's not a problem, because it's really weakly typed. So for Python, you know, no problem. Whereas for C++, as it is strongly typed, you have to be careful about the types. So PMTs is just an answer to this problem, okay? So it allows to exchange data types between Python and C++, okay? So these data objects, you have got a nice page on the GNU Radio website. And if you want to know more about PMTs, the dictionary, and the way it works, it's really well written, because most of the time people criticize the fact that you haven't got a lot of tutorials, it's not well explained, but in that case, you know, they've really done a nice job. So I encourage you to go and see the things about PMTs. So now, what is he doing? Okay. So the transmitter. What we see if we study the block Nordic transmitter, Nordic TX, okay, the message, the input has to be a PMT, and the PMT has to have these data in this way. So for us, channel index, when we've got only one channel, is 0. The channel number, 85. The data rate, 2. The address length, 5. The payload length, 8. The header seconds number, 0. No acknowledge, 0. In that case, the CRC, we use 2 bytes, the address, and the payload. So we would like exactly to mimic what the STM32 does with this transmitter. So the easiest thing to do with this Nordic Tap, we'll have to add this block again. It's a new block. So I'll show you if I find my, it's not this one. I've closed. So remember, the input of the Nordic TX block is a message. So what you can do is to use simply the message strobe block, and you initialize the PMT with the values I've just shown. Okay, that's the easiest way to do it, and you mimic exactly what does the STM32. That's not the final thing, because I use, why do I have to use, yeah, that's an important point. Why do I have to use a message strobe? Do you know why? If you look in the code they've done, it's a loop, a never-ending loop, and they send packet like that. And that's not something that you should do. I want to send a packet every 1 second or half a second. So the message strobe is just a thread that's working, and every half a second it sends a message. And that's exactly what we want. So it's existing, and we're going to use it, and it's interesting. In fact, the message store block, it's the PC clock. It's the yeah. And you see, you have to be careful about the syntax. So it's a VLT in it. It's a U8 vector. Okay, you have to indicate the length of the vector, and the packets vector, which is initialized just here. Okay. So I wasn't satisfied with this, so I carried on with another block, which I found again in the examples. Finally, you see the difference with this one? That's the final one. I've just added a Nordic tap transmitter, and it's easier to play with a block like that because I don't have to have variables, with I just have to initialize my address, my payload in a normal way. Yep. And, to trigger, of course, I've got my message strobe, and it works pretty well. Yeah, I just have to enter my message here, channel and everything, and, in a friendly way.
Friendly user.
Exactly, and this works fine for that. So that's the final thing. You've got everything in the zip. So okay, so that was V5 and V6. Okay. So I gave you almost everything too. Yeah. After that, I've added a tag because I wanted to synchronize my display with the start of the packet. So I added a part in the code, the C++ code. I just added a tag, which has the length of the packet. But you have to be careful about that because your packet is, for example, 36 bytes long. But when you go into the digital domain with the modulation, upsampling and all this, your length has to change. So it would be nice to have something that increase your length you have at the beginning. And for that, you have something really interesting. It's the GR-foo. And this burst tagger block, so you have to install this library. It's you know that you've got 8 bits in a byte, so multiplied by 4 because I take 4 samples. At the end, I must multiply by 32. So I will have exactly the size of the packet in samples after the modulation. Okay, and that's the burst tagger block. And I finish with just one thing if you want to try. And it's the conclusion. This was just an introduction to packet communication, but you've got a nice list of different OOTs to test with packets, and people like Timoshi have gone quite far with that. For example, GR even stream, it demodulates the signal only when you've got an event, and this event is the power you calculate at the input of your receiver, and all the data processing is done only when something comes in. And that's really efficient in terms of speed, okay? And look also at this one. That's a student from EPFL, and it's really nice the work is done about packet communication in GNU Radio. And if you want, also, you've got a dongle, the dongle I was talking about. You can flash the firmware of your dongle, and you can try to sniff people having the same type of mice, and you can see exactly the packets going. And it can become also a transmitter in the 2.4 gigahertz. It sends simply a tone on the 2.4 gigahertz band. So funny things to look at. So I've finished. Thank you very much for your attention. Everything's going to be put on my website, the modified module, okay, and everything.
Yes.
And even how to fiddle with the dongle,
Yeah.
if you want to try it.